طيب، السلام عليكم ورحمة الله وبركاته. حيا الله الشباب، حياك الله يا دكتور.
الله
آه،
يحييك.
طبعا معنا الدكتور محمد نبهان. إن شاء الله اليوم راح يقدم لنا محتوى ثري بإذن الله في اللي هو Introduction of Quality Control، وإن شاء الله راح يتناول المواضيع التالية في المحددة بالبوستر في الإعلان، اللي هو من الأشياء اللي هو Understand Quality Control Concept، من أهم الأشياء، و Get Exposed to Real Life Problems، واخيرا ليس اخرا اللي هو skills needed in the control field. وباذن الله يثرينا الدكتور، والله يعافيكم. تفضل يا دكتور.
الله يعطيك العافية، شكرا على الانترودكشن. بسم الله الرحمن الرحيم. So زي ما تفضل زميلكم, today we will be talking about quality control. This is the outline of the presentation. I'm going to start out with an introduction and history of quality control. Then I will talk about strategic quality control, and I will follow that with the statistical aspect of process control. Following that, I will be discussing advances in quality control in recent years, as well as a walkthrough through data analysis and its relationship to quality control. Finally, I will conclude my talk with a few points on the skills and knowledge needed in this field. So to start off, what do we mean by quality control? And what do we mean when we say we want to improve the quality of something? First of all, we need to identify the dimensions of quality. So there are multiple dimensions and aspects of what we consider to be representative of quality. For example, the performance of a product could be considered a sign of quality. And when we talk about performance, we are talking about the ability of the product to do the job that it's supposed to do. We also refer to reliability as an aspect of quality. And by reliability, we are referring to how well does this product do the job, and how can we rely on it to not break down when we need it to work. Durability is related to the ability of the product to withstand normal use without breaking down. This is also a sign of quality. Serviceability is the ease in which we maintain the product. For example, if you want to buy a car, a lot of the time you think about the maintenance. How easy it is it to maintain this car? There are also subjective aspects of quality, which include aesthetics. So how the product looks like is many times a sign of quality, as well as the features that a product provides. The next concept, which is perceived quality, is a very interesting one because it is both slightly subjective, but it also is rooted within objectivity. And what I mean by that is perceived quality is related to your loyalty to some brand. So for example, consider something like Mercedes or Toyota. So a car company that you trust to have high quality. When they bring a new product, usually you're not very concerned about the quality of the product because you trust the quality of the product. Now, this has a level of subjectivity to it because your decision is not based on certain facts that you've obtained about the latest model, but instead it's based on historical experience, whether it's your own experience or someone else who you trust. And the last one, which is very commonly used in quality control, is, at least in historical quality control, is conformance to standards. And this is mainly considered by the manufacturing company itself or the establishment which provides the service. And it's a test that the quality is conforming to what we think as a company we should maintain. So the Definition of quality, and this definition is considered to be an old definition of quality, is fitness for use. So as long as the product is fit for use, which means that it is doing its intended job, it is the quality of its design is conforming, then it's considered to be a product with high quality. However, the modern definition of quality has been shifted to that quality is inversely proportional to variability. And this is something quantitative. So this is something that we can measure. And to illustrate the relationship between quality and variability, we can consider an example that is commonly used in the beginning of 303 for 3 to 320 for illustration, where a certain part is being produced in two areas, in the United States and in Japan. And on the figure on the right, you can on the figure on the left, you can see the claims of warranty. So these are the claims made by customers for fixing this product. And we can see that the claims that are made in the US are costing much more than the ones in Japan. And the reason for that is that while both processes are centered around the target value of the company, so this is the target value designed by engineers. They want this target to be here. And this target is related to a quality characteristic that represents the part that is being manufactured. So while both processes produce parts that are centered around the target, there's a significant difference in the variability of the produced parts. And so several parts that are produced in the United States may end up being very close to the upper and lower specification limits. And when we refer to specification limits, we are referring to the limits in which products are considered to be good or bad. So outside of these limits, a product is considered to be not fit for use, in which case it might be violating safety conditions. It might just not conform to the design of the engineers, or it might cause dissatisfaction for the customer. And so being outside of these limits for this target quality characteristic is considered a bad thing. And so having higher variability in your process would cause more parts that are outside of this limit. And so this definition of quality improvement then becomes, the objective then becomes to reduce this variability. And as we can see that if we reduce the variability, we eliminate waste and we improve the quality. Statistical methods have been introduced in the field of quality control at different points of the production process. The production process mainly has input parameters, which can be raw materials, components, assemblies, and also in service processes, it could be information. And then in the process, we may have controllable input, which are represented here by the X's, and we may have inputs that are uncontrollable, which are things that affect our process that we cannot control. For example, the weather or the general conditions of the environment. Sometimes we cannot control these variables, but they affect our product and the production process. And once the production process is over, we get some sort of quality characteristic. And this quality characteristic is some numerical value or some description of the product that gives us a sign of the quality of the product. So once the products are manufactured or the service is established, then we look at this output and then we measure it and evaluate it and see if the process is producing high quality products or low quality products. And then applying our decision-making conclusions afterwards. There are several statistical methods that can be used in quality control and at the different steps of quality control. So at every step, there are different methods that can be utilized to improve the quality of the process. Some of these steps are statistical steps, which are related, which are called in the literature statistical process control. And these include control charts, as well as methods for reducing variability and eliminating assignable causes. And generally, it is an online technique. And by online versus offline, the meaning of that is if a method is used while the production process is going on, we denote it as an online method. However, if a statistical method, or any method for that matter, is applied when the process is not going on, so not during the production itself, maybe afterwards or before, we consider it an offline technique or an offline tool. One of these offline tools is design of experiments. Design of experiments tries to consider the key factors that influence the performance of the process. Basically, it tries to relate these Y outputs to the inputs and the raw materials and all the other inputs of the process, whether they are controllable or uncontrollable. Other quality control techniques that are also applicable, whether at the customer level or the supplier level, is also acceptance sampling. And in acceptance sampling, it's generally a procedure where you make decisions about the product that you are receiving or sending, whether it's generally in conformance to your standards or not. There are several influential people in the quality control field who have pioneered a lot of the methods, have been pioneers in this field, and they developed methodologies that are used to this date and have influenced this field greatly. One of these figures is Walter Schwartz, who developed the statistical process control chart, and it was named after him, the Schwartz control chart. And this is a statistical tool that tries to monitor the process online. So here the blue curve, or the blue data points, represent a quality characteristic that is being monitored over time. So at this time period, we get this data point, and so on. And then from this process, we develop some sort of upper limit and lower limit that tell us when the process is going well and when it is not going well. So if these points plot outside of the limit, that is an indication of some sort of problem in the process. Other methodologies that have been discussed in quality control, such as the Schwartz Cycle, which was popularized by Edward Deming, is a strategical aspect of quality control in which we plan or change the experiment's aim to improve the system. So we start with a planning phase in which we identify possibilities and possible courses of action for improving the process. And then in the do phase, we carry out these changes. In the check phase, we study and analyze the results. Do they comply with what we thought the results would be? What do we learn from this experiment? And in the act phase, we adopt the changes that have benefited the process, and we abandon those that have not. And this cycle is a continuous cycle. So it is a cycle that continuously improves our process. So in this sense of continuous improvement, how good is good enough? So take, for example, a process where we have a 99.9%, let's say, conformance to quality. So for example, if you're producing 100 products or 1,000 products, you get 999 good products, and on average, you get one bad product. So if this is the level of quality of your production process, then you have about 1,000 part per million. ppm stands for part per million. So this is the amount of bad products that you're producing in every 1 million products. Now that doesn't sound so bad, but in our everyday life, what if we're talking about wrong prescriptions So when you look at this statistic, you can see that about 4,000 wrong medical prescriptions happen each year. For example, these statistics are from the US. And that is not a small amount of wrong medical prescriptions. So this is fairly a high level of defect. And this is an example of a service case. So this is not a manufacturing system, it's a service system. So this is an indication that quality control techniques also apply to service systems. And another example is the number of flights that have taken too long or too short of landing times, and many other examples. So in these cases, when these errors happen this commonly, then we could still improve on a product, on a process that is conforming 99.9% of the time. And one of the methods that have been popularized to produce results like 13 wrong drug prescriptions or 10 or these very small numbers of defects is one of the methods that have been popularized to achieve this level of quality is what we know as Six Sigma, which is a very popular strategical level quality control model or procedure or philosophy. And the philosophy of this method is to have the standard deviation of the process to be the sixth of the specifications. So essentially, this is where the Six Sigma comes from. The width of this the width of this bell curve that covers the upper and lower specification limits are Six Sigma, which produces 2.002 parts per million bad products, which is a very, very small number of or fraction of defective units when compared to something like a 3 Sigma level confidence or 3 Sigma level quality. It produces 2,700 parts per million. So this is a very, very small fraction of a 3 Sigma level process, which we commonly discuss in 320 as a production standard. So you can see how much of an improvement this would be. But this is not an easy undertaking. This definitely takes a lot of effort to achieve this level of quality. And this is generally an objective that is not regularly met, but it is, you can think of it as a far objective that you continuously work on improving your on your procedure until perhaps someday you get very close to this level. And there are there are a lot of tools that are used in Six Sigma. Some of them are strategical level tools like process mapping, structure trees, Pareto analysis. And also you have statistical techniques such as regression, design of experiments, which we've talked about, as well as hypothesis testing, which is closely related to control charts. So process maps are basically flowcharts for improving the process and standardizing procedures. And control charts and statistical tools related to hypothesis testing look at historical data over time to develop certain procedures. And we also have some analysis and diagnosis tools such as the fishbone diagram, which tries to find the root causes when problems happen. So there are a lot of tools that can be used to improve a process. And once we map the process and we identify the variables that affect the process and have some sort of measuring procedure for the process, and we understand the output quality characteristic as a function of the input quality characteristic, then we would be able to improve the quality of our procedure more and more. And again, most of these quality control philosophies advocate for continuous improvement, where we have some sort of measurement phase, an evaluation phase, an improvement phase, and a control phase. And this is cyclic, in which we keep on improving and attempting to improve the process as it goes on. Again, some of these methods, like design of experiments, is very crucial for improving the process, because you need to establish a good relationship, or you need to understand the you need to understand the relationship between your output and your input very well in order to construct a process that is stable and that produces a certain level of quality, an initial good level of quality that you can improve upon. So, for example, if we have a process where here we have these two types of processes, where the average of these processes are different from our target value, or sometimes the variation is different from what we intended to be, we want to design a process such that it is centered around our desired target value and that has very small variance. And if we are able to understand the relationship between the quality characteristic and our input settings, we might be able to find input settings that produce a type of bell curve for the Y that is both at the target and has low variance. And when it comes to control charts, there are many control charts that are used for different purposes. And that track different types of quality characteristics, such as the defects, whether the number of defects, such as the an average value of the parameter that is being monitored, and as well as cumulative statistics, such as the EWMA and the QSUM, which are discussed by the end of ISE 320. So all of these techniques are generally discussed in ISE 320, and it is the main focus of ISE 320. So you will get exposed to all of these very thoroughly in that course, while DOE is covered in ISE 315. So these are examples of what control charts, different control charts look like. For example, this is a control chart that tracks a variable input X, which takes a real number value. And this is a control chart for the number of defectives, which is an integer type variable, and so on. Now, all of the techniques that we've discussed before, so when you look at this whole chart for control charts, this is still not the this is not even close enough to be a comprehensive list of control charts. Basically, all of this covers the case where you have a univariate quality characteristic. So you are tracking one single Y. So your process may have many inputs, but at the end, you're tracking one particular output measure of quality. And in many cases in industry, or almost all cases in industry, you have more than one quality characteristic that is representative of the quality of the system, sometimes even in the thousands. And this is the challenge in modern quality control issues. So for example, sensing technology has been improved drastically. Now we can get data that profile data, so ones that look like the image here, where we don't have a single Y characteristic, we have a whole curve. So for each product when it's measured, it results in its unique curve, which looks something like this. And this is a zoomed in version of these different parts that represent different aspects of the quality. So they are different key performance indicators. These peak regions are generally considered to be representative of the quality of the product. And these are called data-rich environments. And the reason we call them data-rich is because there's a lot of data condensed within a single observation. So all of this is a single observation. This is one take on a product. And we could have thousands of these curves, and we are trying to see if they are in control or out of control. Are they conforming or non-conforming? And not only this type of profile data, we call this type of data profile data, we also have images and video, such as the picture here on the bottom right. It's a picture from a satellite, and it takes a picture of the sun in an effort to predict or detect the event of a solar flare. And a solar flare is an event where the rays of the sun intrude the atmosphere, and they disrupt, and the rays disrupt the radio technology and causes a lot of issues with signals. And detecting this problem allows us to be prepared for these types of issues. And these types of data result in what we commonly hear these days, which is a contemporary area of research, which is big data, where you have a large amounts of data and you're trying to analyze it and trying to make sense of it. So the availability of data in abundance allows us to have many key performance indicators that can allow us to assess whether a process is going well or not, as well as give us the opportunity to increase the performance and to better utilize the resources that we have. But this comes with its own challenges. An example here, if you look at this particular profile data, it comes from a very complex production process of bucky paper or carbon nanotubes. They are thin sheets of metal, and they are high performance, and they improve, and they are very conductive of electricity. If you've ever heard of carbon fiber, it is essentially how this carbon fiber is being produced. And it's a very powerful material that is widely used nowadays in a lot of production processes. However, it is a very complicated process that goes through several stages. As you can see, these are stages of the production of carbon fiber. And the coming up with a quality control technique that is both online and multi-stage is a very challenging problem. One such method that is non-destructive, and it allows for fast acquisition of data, and it's widely used in nano manufacturing, is Raman spectroscopy, which produces these types of profile data. However, monitoring this type of data is very challenging because the acquisition rate is very high, which means that every second we get a lot of these profiles, and it's a high dimensional profile. For example, for each one of these profiles, we have 512 input variables. So you can think of each one as Y1, Y2, and so on. You have 512 Ys for each acquisition time. And you can see how this can grow, this number can grow very largely as you have a high acquisition rate, which could be 25 per second. You could get 25 per second images of this profile. And a lot of the information is condensed in certain areas. So for example, this specific area and this specific area and the peak. A lot of the times, these are representative of certain quality characteristics. For example, certain variations in this peak mean that we have a certain problem, while certain variations in this peak or this peak indicate the occurrence of a different type of problem in the system. So this type of complex structure is very challenging, and in a lot of cases, you have a lot of outliers which are challenging on their own. Not only that, but many of these systems are dynamic, which means that this curve is not going to have the same values over time. Sometimes it shifts, sometimes it goes to the right, sometimes it goes to the left, sometimes it increases in peak or decreases. And it's not necessarily going out of control. This is just the natural progression of this procedure. And whatever method you apply needs to take into account this natural progression of the data, without saying that it's out of control, because it's a natural change. So these systems are dynamic, they change over time, they're not static. So that presents its own challenges. So an objective would be to come up with consistent methods that are systematic, that are able to model and monitor these issues and detect the changes and come up with a diagnosis which tells us where is the problem. So sometimes we use graphical and probabilistic tools that relate many different variables which are either observed or latent. And these very complex probabilistic models try to simplify the actual process. But sometimes it's even hard to come up with a model that, for every probabilistic model or any type of model, most of the time there's a lot of relaxation of constraints, and there's a lot of assumptions that are being made. So sometimes even the very complex model still fail to represent the true state of the system. This allowed for the emergence, this along with the advent of technology and improvement in data analysis, have resulted in a lot of techniques that are data driven, which means that they don't have, they don't necessarily model the particular system, but they try to learn the model from the data itself, which is where the term data driven comes from. And some of these methods are ones that are very popularized in recent years and that have been used in so many applications, whether it's quality control or signal processing, and many, many other areas such as AI, which is artificial intelligence, and many other fields. But they also made their way into quality control and the ability to detect anomalies. And machine learning generally deals with learning general models, but from the data. So it's a data-driven approach. And data these days, most of the time, it's cheap to get the data. And the data is abundant. We have big data. We have large knowledge databases. However, we don't have, what I should say, we don't necessarily have knowledge within this. We don't understand this data much. We have a lot of data. We have a big knowledge database, but we don't understand the data that well. This is where the role of machine learning and data mining comes in, where we identify novel and potentially useful patterns in the data, and we discover these features and try to exploit them for our objective in whatever application we have. For example, in quality control, this objective might be detecting anomalies. So in machine learning, it's a field that studies algorithms. Algorithms are methods that improve performance of some task. It tries to optimize the performance according to some criterion based on the data and past experiences. Statistics plays a large role in all of the machine learning tools. And it is the base tool that is used, and it helps for inference from the samples. But also a very important area, which is a crucial area in machine learning and data mining, is the role of computer science. And the main role of computer science is to find efficient algorithms. While statistics might be able to present theoretically good procedures, it is not necessarily easy to implement these procedures efficiently. And by efficiently, I mean getting a good solution in a reasonable amount of time. So this is where the role of computer science generally comes in finding out ways to improve the algorithm, make it faster, make it result in faster and better solutions. There are many types of learning methods related to data mining and machine learning. These cover supervised learning, unsupervised learning, reinforcement learning, deep learning, so many other topics. In quality control, the most relevant topics are classification-based topics, which deal with pattern recognition, trying to find out if there is a pattern in the data. And generally, an anomaly or an out of control situation happens because a pattern emerges in the process. Either the mean shifts, the variance shift changes. All of these are considered to be classification problems. And machine learning has been using classification techniques for face recognition. So if you have a quality control problem where you have data and images and you need to recognize some patterns in the images, this is where machine learning comes in. And a very new area in quality control is medical diagnosis. So being able to monitor heart rate, for example, or brain waves, and being able to tell if there's an anomaly or not, if everything is fine or not. These are all areas that intersect between data mining, machine learning, computer science, quality control. It's generally a wide area, an interdisciplinary area. And you can find several people from different disciplines approaching the same problems with different perspectives. And another useful technique for statistical process control is supervised and unsupervised learning. And a very basic supervised learning technique is regression. But other advanced techniques are compression for large data and outlier detection. Unsupervised techniques are used when you don't have an output. You don't have necessarily a Y, which is a quality characteristic that you know of, but instead you just have a lot of X's and you're trying to find patterns within the X's. And this involves clustering techniques where you group similar instances. And if you have an instance that is different from the regular instances, then you learn from this new instance. And another field that is emerging in quality control is popularized by the name data fusion. And fusion is a word that we use for when a lot of things connect and they unite to produce something with more information, with better information. And this is a field that combines a lot of these different knowledge databases that I've been talking about, or knowledge sources, whether it's statistic optimization, signal processing, and quality control, to with an objective of, in the end, we're trying to be able to find these quality characteristics and key performance indicators that improve our process. So to conclude the talk, we talked about theoretical parts of quality control and theoretical fields, which are statistical modeling and optimization. These are two ISE-based routes, and they are used extensively in the field of quality control, especially statistical modeling. But optimization has a big role as well, especially in probabilistic modeling techniques. A lot of the algorithms need to be optimized. And from a technical perspective, with the improvement in technology, data-driven techniques that are related to data science and learning from the data are very prominent, and they produce very good results in practice, such as the field of machine learning. And you can benefit a lot from learning programming languages that are related to quality control and statistics, such as R and Python are two very big areas in which you can improve yourself, and it will work wonders for you in the future because they are very prominent nowadays. As well as simulation in general is always going to be a good technique when you have very complex problems in which finding best solutions is just not practical. So thank you for your time and listening, and I will leave the floor from now on for comments and questions.
طيب شكرا يا دكتور، الله يعطيك العافية. طريقنا صراحة وأثرت الشباب، فإن شاء الله اللي عنده سؤال يا شباب يقدر يكتب بالشات أو يكون عن طريق رفع اليد فيقدر يسأل سؤال. والله يعافيكم جميعا. طبعا يا شباب المادة مسجلة كسيمينار في مادة ISE 390 و 499 والله يعطيكم العافية. أي سؤال بالشات للدكتور أو ارفع يدك يكون المايك مفتوح إن شاء الله عندك. والله يعطيكم العافية جميعا.
تفضل يا أحمد.
يعطيكم العافية دكتور. في عندي سؤال بخصوص اللي هو بروجرامينج. كيف ممكن نستفيد من البايثون بروجرامينج في اللي هو في الكواليتي كنترول and proving simulations?
Python is an emerging language. It's a very popular language nowadays for statistical modeling, and it can be used in all areas of quality control, from feature extraction. And by feature extraction, what I mean is, if you have data, you have these databases, and you're trying to find the model, you're trying to figure out which variables are the interesting ones, which variables are most influential to your process. So بتحاول انك انت تشوف من البيانات اللي عندك ايش الاهم البيانات او what combination produces the quality characteristic that you should track. So Python and R and the integration of the two is very powerful in this aspect, the aspect of statistical modeling and data-driven techniques.
طيب يا شباب، أي واحد عنده سؤال ثاني يقدر يكتب بالشات أو يرفع يده حاليا. إذا ما في سؤال وبعد إذن الدكتور لو تسمحون لنا بس يا هوست تسوي شير سكرين.
أنا اللي أسوي ستوب شير أتوقع.
الله يعطيك العافية. طيب يا شباب بعد إذن الدكتور، هذا سناب النادي، فبإذن الله إن شاء الله بيكون فيه محتوى مثري أسبوعيا إن شاء الله، راح يكون يعني يفيد الطلاب في مجال التخصص، سواء بشقيه اللي هو الصناعية أو هندسة التحكم، ويكون فيه مجالات كثير من متخصصين إن شاء الله ومن أصحاب خبرة، ممكن قد تكون من طلاب بعد. فإذا تأخذون سكرين شوت الله يعافيكم، وشاكرين لكم مقدرين والله يعطيكم العافية، وشكرا لك يا دكتور.
العفو، حياكم
الله يجزاك خير يعطيك العافية.
Yes, definitely, Mohammed. I'm sorry I missed your question. Definitely, process safety is a big aspect of quality control. But generally, I didn't talk about it because safety in general is a huge field that is that is deserving of being regarded as its own, but it definitely bleeds into quality control and quality control techniques. So a lot of these quality control techniques have to consider safety issues and model safety.
طيب شاكرين لك وقتك يا دكتور، والله يعطيك العافية ما قصرت.
شكرا على استضافتكم وعلى المجهود.
أثريتنا الله يعطيك العافية. شاكرين لك مقدرين، وبننهي إن شاء الله السمينار الحين. الله يعطيك العافية. شكرا لك.